Hi everyone, in today's video we are going to continue talking about polynomials and we are going to use synthetic substitution with them as well as the fundamental theorem of algebra. So let's get started. The first thing that you're going to learn how to do in this video is to evaluate polynomials, both using direct substitution, which hopefully will be a review of something you already know, and also synthetic substitution, which is going to be a new method for evaluating. And then after we do that, we are going to learn about the fundamental theorem of algebra so that we can apply it. And we're going to use that theorem to find solutions, factors, and also to write a polynomial equation that is in standard form. So let's get started with the substitution. If you look at evaluating a polynomial, that means we have an x value that we're going to input into the function and see what the y value is equal to. So the first method that you should already be familiar with is direct substitution. So if I have this polynomial, f of x, and I want to evaluate it when x is equal to -2, we're finding f of -2. So we're evaluating the function using that -2 value. So we're going to take that -2 and plug it into the function. So that's -3 times -2 cubed plus -2 squared minus 12 times -2 minus 5. And then from here, this is just simplification. So -2 cubed is -8, -2 squared is +4, -12 times -2 is +24, and I've got that minus 5. So if I keep simplifying, I've got +24 as -3 times -8. Then I'm going to combine these two. That gives me +28, and then I've still got that minus 5. When I combine 24 and 28, that gives me 52 minus 5. So that means 47 is what f of 2 is equal to. Now there are a couple of ways that you may write this answer. The solution in this case, or the evaluated polynomial at -2 is 47. You may also have an answer request that is for you to write your answer as an ordered pair. So that's just this input x value and this output, which is the y value. So you could write your answer as an ordered pair. Or you could also write your answer in what's called function notation. And that's just saying, okay, f is the function that I'm evaluating. I'm evaluating it at -2, and that's equal to 47. So you may also be writing your answer like that in function notation. Okay, so let's move on to the new method, evaluating using synthetic substitution. Okay, so to use synthetic substitution, we're going to evaluate this polynomial when x is equal to -2. It's the same problem as what we just did with direct substitution, so we're still trying to find f of -2. Now, when you use synthetic substitution, the polynomial has to be in standard form, meaning that the leading coefficient and the degree of the polynomial has to be in the first place, and then the exponents are going to go in descending order after that all the way down to the constant term, in this case -5. Okay, so what we're going to do is we're going to evaluate at -2. So you'll notice here I have this L-shaped bar drawn with a little tail on the end, and I put the value that I'm evaluating at outside on the left. So that's what x is equal to. That's my -2 from here. Now for this next line, I'm going to take the coefficients in order from the polynomial. That's my problem. So -3 comes in the first spot, +1, -12, and -5. So again, that's the coefficient for x to the third power, then x to the second power, x to the first power, and then x to the 0 power. So the methodology here is that we are, generally speaking, going to be adding whenever we're working inside of the L shape, and we are multiplying on the outside. So the first thing we're going to do is bring down the first coefficient, -3. And then we're going to start multiply, add, multiply, add, multiply, add, until we get to the end. So we're going to do this -2, this x value, times -3. -2 times -3 is +6. So I'm going to write it in the next open spot. Then I'm going to add. 1 plus 6 is 7, so it goes on the outside. Now I'm multiplying again. -2 times 7 is negative 14. So that goes in my next open spot. When I add these together, negative 12 plus negative 14 is negative 26. And then I need to multiply. Negative 2 times negative 26. That's positive 52. And when I do my last addition, negative 5 plus 52, I get 47. So notice here that my answer, 47, is the same answer I got when I used direct substitution. These are the same thing, just a different methodology. So f of negative 2 in this synthetic substitution is 47. Remember, this is the function notation. You can also write it as an ordered pair, negative 2 comma 47 in parentheses. Okay, so let's try another one of these because I know this is a new topic for a lot of you. So let's look at this problem using synthetic substitution. We're evaluating f of x is equal to negative 2x to the fourth minus x to the third plus 4x minus 5. This time we're doing it when x is equal to negative 1. So that means we're trying to find f of negative 1. That's what we're evaluating. We're going to take the coefficients and write them in descending exponent order, and we have to include all of the exponents. So let's set this up. We've got our L shape with our little tail. The x value of negative 1 is going to go on the outside. Remember, on the outside is where you're multiplying, on the inside is where you're adding. Now we're going to look for our coefficients. The largest exponent, or the highest exponent, is that 4, so I'm going to take the negative 2 and put that in my first spot. And then I have an x to the third. The x, or the coefficient there is negative 1. Now the next one is x to the first power. What's missing between x to the third and x to the first power? Do you see how there's not an x to the second power? That means it's 0 times x to the second, which is why it's missing, because when you multiply something by 0, it's 0. So I need to place that 0 as a placeholder for the x squared term. And then I can do my x to the first power's coefficient, which is 4, and my constant term, which is negative 5. If you forget to include a 0 coefficient where you need one, this is not going to work out nicely. So remember, you can always use direct substitution to check your work. Also, just look at your polynomial and make sure you have all of the exponents starting with your degree and descending order, and it includes all of them. It doesn't skip anything. So let's use the synthetic substitution method now that we've got everything set up. The first number we're going to bring straight down. So that's negative 2. We're on the outside, so we're going to multiply and write our number on the inside now. Negative 1 times negative 2 is positive 2. So that answer goes up there. Then I've got negative 1 plus 2. That's positive 1. Negative 1 times 1. That's negative 1. So my answer goes up there. 0 plus negative 1 is negative 1. Negative 1 times negative 1 is 1. 4 plus 1 is 5. Negative 1 times 5 is negative 5. And negative 5 plus negative 5 is negative 10. Okay, so if I'm writing my answer in function notation here, f of negative 1 is what we were evaluating, and it's equal to negative 10. That last piece. The ordered pair is negative 1 because that's my x value, and negative 10 because that's my y value. Okay, so now that hopefully you've seen a couple of those and feel like with some practice you'll be okay, let's move on to talk about the fundamental theorem of algebra. We have this really important theorem in algebra that says if f of x is a polynomial of degree n, where n is greater than 0, then the equation f of x is equal to 0 has at least one solution in the set of complex numbers. So what that means is if you have some polynomial f of x and it's raised to the n degree, where n is some number like 1, 2, 3, 4, then this theorem implies or says that if x to the n is equal to 0, so we set it equal to 0 and we can solve it, there has to be at least one solution as an answer. Now, a complex solution or complex number, remember, is a plus bi. So this theorem says that you're going to have at least n numbers, or at least one solution that may have some real number in it. It might have some imaginary number in it. Might have one or the other or both. There's a corollary to this theorem that says if f of x is a polynomial of degree n, where n is greater than 0, then the equation f of x is equal to 0 has exactly n solutions, as long as you count each solution, even those that are repeated, as separate solutions. So that means that if you know the degree of the polynomial, in this case n, you know how many solutions there are going to be, how many solutions there are going to be total. If there is a polynomial that is degree n, then it's going to have n number of solutions or zeros. So let's look at a couple of examples. How many solutions does this equation have? Well, the degree of this polynomial, because it's in standard form, is 4. So that means it has exactly 4 solutions. How many zeros, remember zeros are x-intercepts, does the function g of x have? If we're looking for x-intercepts and you know the degree, or not except, let me revise that a little. Not necessarily x-intercepts, but they could be x-intercepts if they're real numbers or imaginary solutions. So we'll go with just the word zeros here. X-intercepts are a type of 0. That means g of x is going to have, because this is a degree 3 polynomial, 3 zeros or 3 solutions. This is going to help us when we need to create polynomial equations and those sorts of things. So there's one other idea that we need to talk about quickly before we get into the actual problems with this, and it is this correlation where we're looking at complex and irrational numbers. If you have an imaginary number, that's an answer, a solution, or you have an irrational number, so the square root of something, a non-pretty number, if you will. Those solutions are always going to come in pairs. So if you have an imaginary number, like a plus bi, then a minus bi is also going to be a 0. If you have an irrational number, like a plus the square root of b, then a minus the square root of b is also going to be a solution. This is because when we use the quadratic formula, you know how there's that plus minus in the quadratic formula? There has to be a positive and a negative version of whatever that square root is, or whatever that simplified square root with the I in it is. All right, so let's look at some examples. If we're given a 0 of the function, that means that x is equal to this number. Identify another 0 of the function. So if I know that negative square root of 5 is one of my solutions, that means positive square root of 5 is also one of my solutions based on this irrational conjugates theorem. If 6 minus 2i is a solution, 6 plus 2i is also a solution based on this complex conjugate theorem. 3 minus 2 square roots of 7 means that 3 plus 2 square roots of 7 is a solution. And if positive 3i is a solution, that means negative 3i is a solution. If we are given factors of a function and we're asked to identify the zeros of the function, that is using the zero product property. We've done this a lot so far. So if we know that we have these values x minus 5 and the quantity x minus 2 that are factors, that means that this can be written as an equation that's equal to 0, and we can split them up. X minus 5 is equal to 0 and x minus 2 is equal to 0 according to the zero product property. That means that x is equal to 5 when I add 5 to both sides, and x is equal to 2 when I add 2 to both sides. So that means the zeros of the function are that x is equal to 5 and 2. Now in this next one, you see that you have the quantity x plus 6 squared. Now with this one, that means that we have x plus 6 times x plus 6. And if those are factors, that means it's equal to 0 and we can solve for x. In this one we get x is negative 6, and this one we get x is negative 6. So notice we get the same answers because of this multiplicity that's happening. This would be a bounce if we were looking at the graph. So the solution is that x is equal to negative 6, but there is this double root or multiplicity of 2. Because technically speaking, there are 2 negative 6's that are answers because of this multiplicity of 2. All right, so let's look at the next one. Using the zero product property, we know that 4x to the third is equal to 0, or 2x minus 1 is equal to 0, if those are both factors. So solving for x, we divide by 4 on both sides, and then take the cube root of both sides. So that's going to give us x is equal to 0. When we add 1 to both sides on this one, and then divide by 2, that gives us 1/2, which means x is equal to 0 and 1/2. Okay, this next one, 3x minus 1 is a factor, so it might be equal to 0, or 6x plus 5 is a factor, so that's equal to 0. That means x is equal to 1/3, and x is equal to negative 5 divided by 6. So our zeros here are 1/3 and negative 5/6. All right, the last thing that we need to do with this piece is if we're given a list of zeros, can you write the list of factors? So we're working backwards from what we just did in 5 through 8. If we know that x is equal to 5 and negative 8, can we write 2 factors, 2 sets of parentheses? We know that the sign is going to change when we move it over to the same side as the x. So when we subtract 5 from both sides, for example, it's going to leave a 0 there. Which means that x minus 5 is equal to 0, so that's one of our factors, and x plus 8 is the other factor. If x is equal to plus and minus 6, that means x is equal to 6, and x is equal to negative 6, which means x minus 6 is one of the factors based on that solution, and x plus 6 is another factor based on x is equal to negative 6 when we add the 6 over so that it's set equal to 0. Okay, for this next one, let's look at this x is equal to negative 1 over 4. If we're trying to get it equal to 0, we multiply by 4 on both sides. That gives us 4x is equal to negative 1, and then we need to add 1 to both sides. So that gives us 4x plus 1 is equal to 0. So one of the factors is 4x plus 1, and the other factor, if x is equal to 5, is x minus 5. Something that I want to point out here, if you're looking at this 0, notice that the sign changed and the denominator moved up to be with the x value. That's a nice little shortcut that you can use whenever you have fractions as solutions. Okay, let's look at this last one. We know that x is equal to positive 2 square roots of 3 and x is equal to negative 2 square roots of 3. So if we are writing those both as factors, we're going to have x minus 2 square roots of 3 and x plus 2 square roots of 3. Because if I split those up, in this one I'm subtracting 2 square roots of 3 from both sides, which gives me x minus 2 square roots of 3 is equal to 0. And in this one I'm adding the 2 square roots of 3 to both sides, which means I have x plus 2 square roots of 3 is equal to 0. So there are my 2 factors. Okay, so let's apply some of this information. In this next problem, you're given a list of zeros and told, okay, write the polynomial function now. So we have to take the x-intercepts that we know in this case, because they're all real numbers, and we have to take this leading coefficient of 1 that we've been given. So there are 2 pieces of information there that I've underlined. We know the leading coefficient is 1, and we know the x-intercepts. So if we're looking for what degree this polynomial is going to be, if we know that there are 3 solutions, that is the degree as well. It's a 3rd degree polynomial because the number of solutions, the quantity of solutions, is going to match the degree of the polynomial. So we can figure out our end behavior now with this 3 and this leading coefficient of 1. The 3, the degree, is an odd number, and the leading coefficient 1 is a positive number. So that means if it's odd and positive, it's going to be opposite directions and an increasing line. generally speaking. So the end behavior as x approaches negative infinity, that's the left-hand side, our function f of x is going to go down to negative infinity. And as x approaches positive infinity, that's the right-hand side, it's going to go up to positive infinity. The first thing we're going to do is take our zeros now and write them in factored form along with the leading coefficient. So let's write a polynomial function. Our leading coefficient is 1, and then if I turn each of these zeros into factors, that's going to be x minus 4 times x minus 1 times x plus 2. Okay, so I've written everything as factors, and now the directions are asking me to convert to standard form. So I'm going to use polynomial operations here and do a bunch of distributing because I have 3 factors that I need to multiply together. So I'm going to multiply together these first 2 as this first step here. X times x is x squared, then I get minus 1x minus 4x plus 4. Okay, so I've multiplied together the first 2. I'm leaving off this leading coefficient of 1 because 1 times anything is just itself. And then this x plus 2, I can't forget about it. I'm going to need to multiply him in a few minutes. So let's combine the like terms and then we'll multiply together the trinomial with the binomial. Got x squared minus 5x plus 4 has my trinomial, and x plus 2, which I'm about to distribute in. Okay, so let's do some distributing on steroids here. I'm going to take this x and distribute it first. X times x squared is x to the third. Then I'm going to distribute it to the negative 5x, so that's negative 5x squared. Then I'm going to distribute it to the 4, so that's positive 4x. Now I'm going to take the 2 and I'm going to do the same thing. 2 times x squared is positive 2x squared. 2 times negative 5x is negative 10x, and 2 times 4 is positive 8. All right, do we have any terms that we can combine? It looks like we have some x squared terms, and it looks like we have some x to the first power terms. So let's combine these now. We have x to the third minus 3x squared minus 6x plus 8. That is it looks like that is in standard form. Yep. So this is our standard form polynomial given only the leading coefficient and the zeros. Now let's graph this over in the side. We can find the zeros, or we have the zeros. Those are x-intercepts. So we can graph negative 2, positive 1, and positive 4. And then we can use our end behavior, negative infinity up to positive infinity, and our multiplicity to get this shape. All of these factors are to the first power, which means they're all going to cross, right? So when we graph this, we're going to start down at negative infinity on the left. We're going to cross through negative 2, and we're going to cross through 1, and then we're going to cross through 4 and go up to positive infinity. If you want to find the y-intercept, we're evaluating at f of 0 because that's where the x value is 0. So if I put that into f of x here, look at what's going to happen. 0 to the third is going to be 0. X squared is going to be negative 3 times 0. Negative 6 times 0 is going to be 0. And then you've got that plus 8. So the 0 to the third is going to disappear. 0 squared is going to make this negative 3 disappear. And negative 6 times 0 is 0. So that's going to leave me with just 8. That means my y-intercept is 0, 8. So that's this point here. We can label it. If you want to verify to make sure that you got these correct, you can always graph in the calculator. So let's graph this answer that we got and see if it matches this graph that we just roughly sketched here. So in my y equals, I am going to plug in x raised to the third power minus 3x squared minus 6x plus 8. When I graph that, look at that. I've got an x-intercept at negative 2, positive 1, and positive 4. It looks like the y-intercept up there is at 0, negative 8. So that looks good. My graph is correct. All right, so let's look at another one of these that's a little bit harder. Let's find a polynomial of least degree where the leading coefficient is 1. Notice that's a positive leading coefficient. And it has zeros at 5, 3, and negative 2i. Now, with this one, you've got to be really careful because you need to identify all of the zeros. It left one off of the list. We know that x is equal to 5 and 3. It's also equal to negative 2i, but do you remember that corollary that we talked about a few moments ago? If the negative version of an imaginary number, complex number, is one of our solutions, the positive version of that complex number is also one of our solutions. So that means we need to identify another zero that's in our list. Remember that you only need to do this when you have a complex solution, meaning that there is an imaginary number in it, or when you have an irrational, meaning that there is a square root in one of your zeros. Okay, so if we have 1, 2, 3, 4 solutions, that means the degree is going to be 4. That's an even number, so now we know our end behavior. If it's an even, both ends go the same way. If it's positive leading coefficient, they both go up. So the end behavior on both ends, left and right, are going to be positive infinity. So now we're ready to write our factored form and then convert it to standard form to get our polynomial. So let's write our factored form using our zeros. We're going to take each one of the zeros, all 4 of them, and turn them into factors. So that's x minus 5, x minus 3, x plus 2i, and x minus 2i. Remember, the signs change when you take a zero and write it as a factor. To convert the answer to standard form, we need to do some distributing, some foiling. I'm going to combine these first 2 by multiplying, and I'm also going to combine these second 2 by multiplying in this next step. So I've got f of x is equal to, and I'm going to FOIL these first 2 together first. X minus 5 times x minus 3. That gives me x squared minus 3x minus 5x plus 15. And then when I distribute or FOIL together the last 2, I get x squared minus 2ix plus 2ix minus 4i squared. Now, I want to pause here for just a second because this last bit of distributing that I did, a lot of people have been making mistakes there. So when I do my first, that's x times x, which is x squared. When I do my outer, it's x times negative 2i, which is negative 2ix. My inner is positive 2ix. And this last one is where people have been making a mistake. When you multiply 2i times negative 2i, you're doing 2 times negative 2, which is negative 4, but also I times I, which is I squared. That is going to simplify because remember, I squared is equal to negative 1. So I'm going to have to substitute in a negative 1 right there, and when I do that, negative 4 times negative 1 is equal to positive 4. So that's going to change when I write out this next line combining my like terms. Let's combine like terms. In the first expression here, we've got x squared minus 8x plus 15. And in the second expression, these 2 add together to 0, so it leaves us with x squared, and then like we said, this is negative 4 times negative 1, which is positive 4. Okay, so now I'm ready to do some distributing again. We're doing that distributing on steroids thing where we do lots of distributing, more than just FOILing. So we've got x squared times x squared, that's x to the 4th, x squared times negative 8x, so that's negative 8x to the 3rd, x squared times 15, so that's 15x squared. When I distribute the 4 times x squared is positive 4x squared. 4 times negative 8x is negative 32x, and 15 times 4 is positive 60. Looking for like terms, it looks like we have some x squared terms to combine, and that's it. So we have x to the 4th minus 8x to the 3rd plus 19x squared minus 32x plus 60. And that is in standard form because my exponents go in descending order. So that is my final answer for this polynomial. Remember, if you want to find the y-intercept, you're evaluating f of 0. And this x is going to be 0 to the 4th. This is going to be 0 to the third. So that's just going to leave us with the 60 as our y value. So our ordered pair is going to be 0, 60. Okay, so let's do some graphing. The real numbers that we know, the x-intercepts, are 5 and 3. So if this is 3 and that one is 5, let's graph now. Our ends both have to go up to the positive, and because all of these were first powers, the multiplicity means that we are going to cross at each of the x-intercepts, 5 and 3. So we're going to start up here, we're going to go down, there might be something weird that happens down there, and then it's going to go back up to cross again. The y-intercept is going to be at 0, 60, so it's going to be way up here somewhere when this comes up. Okay, and if we look at our graph in the calculator, or function in the calculator, let's plug that in to see how close we got on our rough sketch. We have x raised to the 4th power minus 8x raised to the 3rd power plus 19x squared minus 32x plus 60. When we graph, let's see how close we got there. All right, look at that. It looks like it is going through 3 and 5, so that's good. Both ends go up, and if we zoom out by hitting zoom and then choosing option 3 and hit enter, it'll zoom out and we'll be able to see a little bit more to see what's happening with that graph. Look at that. It looks like there's a parabola. There may be something weird going on down here. We could zoom into just this area if we wanted. For our purposes, though, right now, I think this is adequate enough to say a rough sketch is pretty good. Okay, so we have in this video learned about evaluating using both direct substitution and synthetic substitution, and then we also found solutions, factors, and wrote polynomial equations in standard form by using that fundamental theorem of algebra and the corollaries that go along with it. Take a few minutes now to try the Now You Try problems for us to talk about in class.